In the last lecture, we said that the properties of a pure substance can be obtained in various ways. One way is through the use of property tables. That's what we did extensively in the previous lecture, wherein we considered substances such as water or refrigerants, wherein the property tables are available to us. But what about those substances or conditions of substances, specifically gases, wherein the property tables are not available? And so to be able to retrieve the properties for those conditions, then we'll be using another method, and that is through the use of equations. And then note that since we can retrieve the properties whether using property tables or using equations or using charts, that means that whatever method that we'll be using, whether using property tables or equations or charts, more or less the value would be the same. So that is our reason for having this topic number 4, which is about the retrieving the properties of gases at some particular conditions. So take note at some particular conditions because it says here ideal gases. So for the context of this presentation, first have an introduction. As usual, we have to define properly or describe properly those conditions wherein the ideal gas assumption would hold true, and then we will define what is an ideal gas, and then we will introduce the equation of state for these ideal gases. Then for topic 4, subtopic number 4 here, the compressibility factor. So what about those gases wherein it's not, or it does not follow this ideal gas behavior? Then how can we solve it if we want to use this equation of state? Then we'll be introducing the compressibility factor. And to obtain this compressibility factor is to use a compressibility chart. So now for the introduction. For some substances, as we have said, that there may not have property tables available to us, and so the use of equations is rather more convenient. And those gases examples are argon, oxygen, hydrogen, or typical gases that we have in the table of elements in the chemistry. So those gases at A conditions, that's for ideal gas. So we say conditions, we have here the pressure and temperature diagram, also called as the phase diagram, because it shows the various states of the pure substance across a wide range of temperature and pressure. And we have here a point. That point is what we call the critical point. So it's critical because beyond this critical point, beyond the critical temperature and the critical pressure, then the distinction between the liquid and gas is it can be no longer be distinguished. So we term it supercritical fluid. So beyond that point. So for gases that have a very, very low pressure or very, very high temperature, or maybe can have both, relative to the of course relative to the critical point, then we can assume that it is an ideal gas. So at these conditions we can say that or that's what we mean when we say ideal gas. We are only referring to the gases at these conditions very, very high relative to the critical point. So very, very high and very, very low pressure relative to the critical point. So take for example here an air. So air, the critical pressure of air is 3,770 kilopascals, and the critical temperature is 132.5 Kelvin. Now convert this to Celsius, I think, so minus 273, so I think around it's minus 140 degrees Celsius. So that's the critical temperature of air. But the ambient temperature is around 30 degrees C. So here the 30 degrees is very very far from this negative 140 degrees. We have a 0 degrees C here. So that means that at ambient conditions, then the air, we can consider it as an ideal gas. So also for the critical pressure, it is 3770 kPa, and ambient condition is only around, the atmospheric pressure is around, of course atmospheric is 101.3. That is relative to the absolute, so this is already absolute, so 101.3 kPa. So we have a pressure that is very very low as compared to the critical pressure. So those are the conditions for this assumption. Now, technically, when you say ideal gas, it is a simple compressible substance. It is a pure substance. It is an assumption or an idealized pure substance that has a behavior of PV over T is equal to constant. The pressure times the volume, and this is the specific volume all over the temperature is equal to a constant. So that's the behavior of these ideal gases. Now, on the basis of experimental work carried out by various scientists, so they experimented and they have observed that, let's say we have here a gas in a piston cylinder device, and it is maintained in a constant temperature. So at T is equal to constant, T is equal to C. So notice here we have a pressure at this state or at this condition, and we have the volume. So we have pressure here, we have volume. And then if we apply a force, so if we apply a force here, then of course there's a change in the pressure, and there is also a change in the volume. So you can see the volume gets smaller. So increasing the pressure decreases the volume. So by plotting this in a diagram, the volume pressure diagram, we have this curve, and that means that at constant temperature, at T is equal to C or constant, the volume is inversely proportional to the pressure. Inversely proportional. That means at higher pressure we have lower volume, or at lower pressure we have higher volume. Okay, another scientist experimented on the same gas, but it maintained a constant pressure rather than the temperature. So that means at these conditions we have this volume, and we also have the pressure here. So pressure and volume. So what will happen if we add heat to this gas? So because gases will expand, so the molecules will the energies in the molecules will be more energetic. So that means it will try to push this piston, and assuming that we can have a freely moving pistons, then that means that it has to expand. So that means the volume will expand. So by plotting this in a graph of a volume and temperature graph, then they have found out the volume is directly proportional to the temperature. So at lower temperature we have lower volume, but at higher temperature we have higher volume. Then another experiment using a constant volume process. So that means that the piston face here is fixed all throughout the process. So it's fixed here, and then it's also fixed here. So first is we have, of course, we have a temperature. We have a temperature here, and we also have a pressure, temperature and pressure. Now what will happen if we increase the temperature? So we add heat to the gas, then what will happen to the pressure? So by plotting it again in the graph, pressure and temperature, then they have found out that pressure is directly proportional to the temperature. So that means at lower temperature we have a lower pressure, but at higher temperature we have a higher pressure as well. So this is true for constant volume process. So V is equal to constant, and here pressure is equal to constant. So that's how they arrived to these equations. The PV over T is equal to a constant. Now, for an ideal gas equation, that constant is the specific gas constant. And we use the symbol R for that. So that depends upon what type of gas is in that cylinder. So if it is air or if it is oxygen or whatever gases, it has a specific gas constant. And that constant can be obtained using tables right here. I mean, it is a tabulated data. So for gases, say air, and here's the value of the specific gas constant, 0.287, and the unit is kilojoules per kilogram Kelvin. And I have also included here the moles. Okay, then for nitrogen, we have another values for specific gas constant. So that means that the specific gas constant is actually unique for each kind of gas, or each type of gas. Okay, so PV over T is equal to constant, and if we replace that constant by R, then we can have, actually we can express this in various forms. So multiply both sides by temperature, then what you get is PV is equal to RT. So take note that for now we are using the specific volume, and the unit is cubic meter per kg. And if we're using specific volume, then that means we can have this expression of the ideal gas equation. PV is equal to RT. And then if we use the total volume, then that means since this one is just equal to total volume all over mass, then since PV is equal to RT, so convert this to total volume. P is equal to RT. So multiply both sides by M. We have PV is equal to MRT. So in this case, we have a total volume. So we have total volume. And then since mass of a matter can also be expressed in terms of moles, and the relationship is just simply this. So N is the number of moles, is equal to the mass in kg divided by the molecular weight, or actually molecular mass. This is kilograms per k mole. So right here, that's the reason why I included a column for this. The mole of a particular gas. So for air, this is the moles. For nitrogen, this is the moles. Kilogram per k moles. And the oxygen, this is it. So again, it's specific to a specific gas. So if we are using this, if we substitute the mass here, so let's say mass is equal to the number of moles times the molecular weight, right? So from this expression, we can derive this. Mass is equal to the number of moles times the molecular weight, or molecular mass. We substitute it here. What we get is actually PV is equal to NMRT. But then they have found out from experiment that this product of the molecular mass times the specific gas constant, so let's say air, so the product of the molecular mass of air and the specific gas constant of air, so the product of this M and R, so this one, the product that is actually constant to all type of gases. So we'll take this product of this, the product of this, then more or less the value is a constant. So R times M, we have a constant value, and that constant value is what we call the universal gas constant. Universal gas constant. We use the symbol R, U. That means it is it is the same for all types of gases. That's why we say universal gas constant. And the value in these units is 8.314 kilojoules per k mole Kelvin. Okay, so um, again, we can have expressions for this. We can have expressions for specific volume using specific volume, or using total volumes, or using moles. Okay, so now let's have a sample problem for this. For our first sample problem, we have here, it says 2 kg of air at 280 Kelvin are contained in a 0.2 cubic meter tank. Consider the air to be an ideal gas and determine the following: the pressure, the number of moles, and the specific volume in mass basis and molal basis. And this problem is taken from one of our reference texts by Sanchel and Bowles, 2024. Okay, so for the solution, first step, as usual, is to illustrate the problem. So illustrate the problem. Illustrate the problem. Okay, so we have an air that is inside a tank, and the tank is, the given here is a volume, so that means it is a solid. So you can have let's say cylinder, cube, or whatever. So let's say we have a tank that is in a cylindrical shape. So the volume, or the substance here, is air, and the given properties, we have mass of 2 kg, and we have temperature of 280 Kelvin, and we also have a volume of 0.2, so volume of 0.2 cubic meters. Okay, so we have here, it says ideal gas. That means we'll be needing, okay, so from the tables, and when I say the tables right here. So in the appendix, I have included a table, properties of some ideal gas. So we'll be needing the value of this R. So that is 0.287. So from table, so R is equal to 0.287 kilojoules per kilogram Kelvin. Okay, so now let's apply, or let's solve if we can. So the pressure, solve for the pressure. Okay, solve for the pressure. So apply the equation using, let's say, using ideal gas equation. So P is equal to or PV, and we'll be using the total. Okay, total PV is equal to MRT. So since we have the volume, we have mass, we have the specific gas constant and temperature, then we can solve for pressure. By the way, when applying ideal gas equation, take note that the temperature must be in this must be in absolute temperature, and also the pressure. So absolute temperature. So that means if the given unit is in degrees Celsius, then you have to convert it into Kelvin. So pressure is equal to mass times the RT over V. So now substituting the values, we have 2 kg, then 0.287 kilojoules per kilogram K, and the temperature of 280 K. So 280 K divided by the total volume of 0.2 cubic meter. Okay, so let's calculate 2 times 0.287, okay, times 280 divided by 0.2. This is equal to 803.6. 803.6, and the unit is in kilopascals. So for the units, let's check. Here it says kilogram, so kilogram cancels out. We have Kelvin here and Kelvin, and what's left to us is kilojoules per cubic meter. But what is kilojoules? So kilojoules is kilonewton meter. So meter raised to 1 divided by meter cube, you have m squared at the bottom. So that means our unit is kilonewton per meter squared. And what is this? This is kPa, kilopascals. Okay, the next is the number of moles. So for the number of moles, we have N is equal to the mass in kg divided by the molecular weight. What is the mass? 2 kg, and the molecular weight is 28.97. We have here 28.97 kg per k mole. So 28.97 kg per k mole. So 2 divided by 28.97. This is 0.069. So 0.069, and what's the units? So cancels out kg, we have k mole. Okay, the next is the specific volume in mass basis and molar basis. So the specific volume in mass and molar basis, or in mass basis first. So in mass basis is the specific volume mass basis is, so V is just equal to the total volume divided by mass. Total volume is 0.2 cubic meter per divided by 2 kg, and this is 0.1 cubic meter per kilogram. Okay, the next is the specific volume. Okay, the specific volume in molar basis. So I think we must divide the total volume with the number of moles. V, total volume divided by the number of moles. It's not, I think for mole basis it must be the number of moles. So 0.2 cubic meter divided by the number of moles, 0.069 k mole. 0.069 k mole, and the value here is, so 0.2 divided by 0.069, we have let's say 2.89. So 2.89 cubic meter per k mole. Okay, so I think the problem we have here is just straightforward, because we are given with these states or properties, that these states or conditions, and we just apply directly the ideal gas equations once you have this specific gas constants. So once you have that, then you can find the other properties. Okay, so next problem. So next problem that we have comes from this one of our reference texts. Says here 3.5 kg per second is a mass flow rate. So kilograms per second, that means is a mass flow rate. Flow rate of air at 100 kPa and 25 degrees Celsius is to be introduced into an air compressor the air will exit the compressor at 800 kPa and 300 degrees C with the same mass flow rate. Using the ideal gas law, determine the volumetric flow rates at the entrance and exits. So our system here is an air compressor. That device actually compresses air. Increases, when say compresses air, that means it increases the pressure. As you can see here, starting from 100, then it goes to 800 kPa. So we are just asked to solve for the volumetric flow rates. Okay, so first step is to, as usual, illustrate the problem. Illustrate the problem. So to draw the compressor, the symbol for compressor is this one, and then we have this shaft right here, and then air will enter at this inlet and then will exit at this outlet. So we have a mass entering the system and mass exiting the system. Of course, we need to define our boundary. So here is the boundary. And say this is point 1, that's the inlet, and here's the point 2. So at point 1, that's our inlet, and the given value of mass is 3.5 kg per second. It says here 3.5 kg per second. And then the pressure is 100 and temperature is 25. So pressure is 100 kPa, then temperature is 25 degrees C. In this condition, point 2, it's the outlet, and the mass is still the same, 3.5 kilograms per second, but the pressure and temperature are now different. So 800 kPa and 300 Celsius. 800 kPa and what was that? 300 Celsius. So 300 Celsius. I think I have to change the position of this and also this. Okay, so here's our inlet. So inlet conditions and outlet conditions. The substance is air. So substance is air. And the specific gas constant is 0.287 kilojoules per kilogram Kelvin. So the problem says, using the ideal gas law, determine the volumetric flow rates and at the entrance and the exits. So we need to solve for the volume using ideal gas equation. So next step is say at inlet, the volumetric flow rate can be obtained. Volumetric flow rate can be obtained by okay, so recall PV, we will be using total volume. Okay, PV is equal to mRT. Since we have pressure already, pressure is given, mass is given, but in terms of flow rate, so we use m dot, that means it is in terms of flow rate, and R, there's a value for R, and the T is also given, so therefore this can be solved directly. So m dot R T all over P. Substitute the values. We have 3.5 kilogram per second. So kilogram per second, or I'll just write the units later, and then 0.287 and 298. So 25 plus 273. So the temperature should be in Kelvin. So 25 degrees C, so plus 273, that is 298 Kelvin. Okay. All over the pressure of 100 kPa. 100 kPa. So 3.5 times 0.287 times 298 divided by 100. So this is 2.99 cubic meters. So answer here is, okay, let's just say 3 cubic meters per second. So that's the volumetric flow rate. So by the way, whenever we have a flow rate, so for mass we use m dot, but for volume we'll be using m dot as well, because it's a flow rate. So flow rate, that is per unit time, so 3 cubic meters per second. Okay, next is at the exit. So at the exit, so we still apply the same equation. So PV is equal to MRT. So V dot is equal to M dot RT over P. What is M? It's still the same, 3.5, and R is 0.287, and the temperature now 300 plus 273, that is 573 Kelvin. Then divided by the pressure of 800. So let's check. 3.5 times 0.287 times 573 divided by 800. We have 0.719. 0.719 cubic meters per seconds. Okay, so far we have dealt with this simple problem. So just simply plug and compute the values. And also we can notice that the ideal gas equation, this can also be expressed in terms of flow rates. So if this is m dot, that means this will be v dot. So in the next video we'll discuss the compressibility factor, so for those gases that can't be assumed as an ideal gas. So see you in the next video.